Alright, do we really have such media? Right? Do we really have such media? That is the question. Now, the point is, yes, we do have it, and this is not very modern optics. People knew about these kind of this kind of a scenario, that in certain crystals, okay, look at this particular crystal, okay, focus on this panel. Here you see a crystal. Apologies for the poor contrast of the image. It is actually it's a live example I picked up from hyperphysics. Credits to them. Now, you see a dot over here on a piece of paper present beneath the crystal. The crystal is placed on it, and you essentially now see just one dot. All right. Now, in panel 2, that is this panel, look carefully. The crystal has somehow been rotated, okay, and you see two dots here. Why? Because one ray, the ray that we are viewing from the top here, is essentially has a source point underneath. When it enters into a medium, let us say, maybe I should put it at an angle. I should exaggerate this, maybe, perhaps. Enters the medium at an angle, and the ray bends, and it bends into two pieces owing to NO and NE being having two different values. We will see some typical values of NO and NE for crystalline media like quartz and calcite and so on and so forth, and we are viewing the beam from this direction, right. So, if I now had a bundle of rays originating from an object here, a viewer viewing this from this side would essentially see two of those objects because of birefringence. Okay. It is like seeing maybe two reflections, one from the front surface of a glass and one from a rear surface and so on. These are phenomena that the birefringence is not a phenomena we encounter commonly in day to day scenarios, right. But this was owing to this fact that you get two sets of rays arising out of one set of source rays from an object. This phenomenon was called double refraction, and it was discovered long ago in certain crystalline stones. The interesting thing is, and this is a demonstration I like to show students in the class, you take a piece of calcite and put a dot of ink on a paper underneath and rotate the crystal. You actually see that while one dot stays where it is during the rotation, the other guy, due to the extraordinary ray, tends to circumambulate that. Okay. There are nice illustrations of this on public media such as YouTube. So, I would encourage you to look at that. So, double refraction or double is bi. So, double refraction is of course bi refringence can happen. Now, why are we discussing birefringence in this course? Because we have hope to maybe get here. Yeah. Okay, now can I achieve so called phase matching? What is phase matching? N of omega is somehow equal to N of 2 omega. So, let us examine these scenarios. Remember that in a birefringent medium, refractive index depends upon the direction that the k vector makes with respect to the optic axis theta, as 1 over n square is cosine square of theta divided by no square plus sine square of theta divided by ne square. Now, consider such a medium. Optic axis is a direction. In principle, I do not need this second axis at all for this discussion. Okay, I just need to pick a point of reference. Now, consider the ordinary refractive index of the medium. The ordinary refractive index of the medium is, as I said, for a beam with optic axis z, the ordinary refractive index does not matter. The ordinary refractive index remains the same independent of the angle. Okay, angle the k vector makes with respect to the optic axis. Whereas the extraordinary component, okay, Ne of omega, the extraordinary refractive index depends upon the direction that the k vector makes with respect to the optic axis, right. It can take values based on theta to be value here, value Ne here, and so on and so forth. So, both these were plotted for, or rather I should not call this the extraordinary refractive index. The dotted ellipse is essentially the refractive index as seen by the beam in the real anisotropic uniaxial medium. So, this is the refractive index curve for the beam in this medium. Now, this Ne at omega, No at omega and Ne at omega mark or define the system. These two values of N naught or No and Ne are what define everything at a given frequency omega. Now, let us ask the question about what happens to the same at the frequency 2 omega. Where is No? If for No, okay, if for No we have the fact that No of 2 omega has this circle, okay, the green dotted circle, and Ne is less than No at 2 omega, then all the values of refractive index n of theta for 2 omega will lie on this ellipse, right. This is a scenario where in particular for this medium No is greater than Ne. We could also have media where it is the other way around, right, both at omega and at 2 omega. Okay. So, this condition is moot here, No greater than Ne at over a reasonable range of frequencies that we are interested in here. Now, what is the point of all this? The point of all this is the following. If I chose now this medium and propagated the wave along the optic axis, okay, I match the optic axis of the medium with the vector k, then look at this, there is such an angle, okay, at which n ordinary of omega and Ne of theta at 2 omega match. So, along this direction, along this particular direction, these two quantities match. This is what we were seeking. So, we have n ordinary of omega being equal to any 2 omega of a particular theta at a special theta we call theta m. This condition happens to be satisfied, phase matching condition is satisfied. It is purely a geometric thing, but we have to choose appropriate media. It is hinged upon these numbers NO at omega, NE at omega, NO at 2 omega, NE at 2 omega, all right, of the medium whose chi 2 is of importance here. So, that nonlinear medium should have this case. Then by launching the omega beam, the pump beam at a particular angle, we will get the second harmonic emanating at an angle theta with respect to the optic, or theta m with respect to the optic axis. So, theta m is the appropriately called the phase matching angle. Okay, it is a special angle determined by the optical parameters of the medium. So, phase matching is indeed possible and realizable in uniaxial media exploiting the birefringence of that is offered by nature. Okay. So, what have we done? We have therefore picked a medium where, although there is dispersion, refractive index does increase with frequency for this medium. It is normally dispersive, but then we have ordinary and extraordinary refractive indices. Now, what we have done as a consequence of phase matching is we have made the extraordinary refractive index of at omega match with the ordinary refractive index at 2 omega. This is the trick that we have played, all right. And the extraordinary polarization for omega and the ordinary polarization, the refractive index and the extraordinary polarization for omega and ordinary polarization of 2 omega were matched. So, this is one type of phase matching. Okay. The ordinary and extraordinary refractive indices for these crystals are different only by about 10%. If we take a nominal refractive index value of 5 to 10%, refractive index to be say 1 point something to 2 point something, they differ. The delta of NO minus NE is just about 0.1, all right. So, this is essentially what we have done. Okay, sorry, I misrepresented this. By tuning with the angle, sorry, this is what we did. By tuning the angle, we tuned this entire curve down so that the refractive indices can match.